Today for research at TTIC, we have Anand.B, a research assistant professor here working on exciting things in computer vision. And yeah, today he's going to tell us about generative image models inside out. And so I think we'll turn off the lights so that you can see all the cool things.
All right. Thank you very much. Thanks for coming, and I hope it's not too me, but I would really you would really appreciate the result that I want to show in the dark setup. Okay. With that, I want to get started. Today, I'll be talking about generative image models, and most importantly, what we can discover inside them as an emergent property and some surprising insights. So, for people who don't know me, like Abdul said, I am here. An RAP. I started last year in September, so it's been like about 18 months here now. And I mostly work on lighting, geometry, and 3D awareness in computer vision. For today, I will be talking about how we can learn about this phenomena using generative image models. Why generative image models? We all know that we are in the midst of what I call digital renaissance, like not just in image model space, but also in all sorts of generative modeling space. We now have several tools with which it's difficult to imagine that we can live in today's world. So for example, I believe everyone uses ChatGPT for various things, either to get a boilerplate, for fine tuning, or getting some insights. Or even the Google search, which we were used to, is completely getting disrupted by several players like Perplexity. Instead of getting links, now we directly get answers to our questions by querying. Not just that, even the paper recommendation systems have gotten better using some tools like Scholar Inbox, where you get like a catered, personalized recommendation system using this large language models directly to your emails. Even the way we write code has changed. Cursor, GitHub Copilot, there are several other tools where you can automatically write codes very quickly. And lastly, the image generation has completely changed over the last few years because of tools like Midjourney. Here is an example that I want to show. This is from 2022, not even recent times, 2022. Midjourney early version. If someone had told me this image is a generated image, it would be very hard to imagine. You can see the water droplets near the eyes, the hair strands, and so on. They all look very hyper-realistic. It's very hard to see that this image is generated. And it's very difficult. It's very hard to find any inconsistency in these images. So the way I see it is, we can now generate images as if we are switching on a water tap. Like you just give an input text prompt, and the output that you get is an image generated. So here are three chosen prompts that I chose. Like one is a living room, indoor scene, and the other is an outdoor scene. And in the middle you see is a modern futuristic city. So what I want you to focus on is the highlighted parts, that is about lighting. The model seems to understand very complex phenomena, something like lighting. So here in this, we say that, okay, the image should have a sunlight streaming through windows. You can see that there are lots of windows and sunlight is streaming through. In the last one, you see that a mountain landscape at the sunset. It's very hard to see whether it is sunrise or sunset, but one simple cue to notice is that if there is an orange cue instead of a blue cue, you can see that it's a sunset instead of a sunrise. In the middle, you see like futuristic city with neon lights. Not just image generation, even now we can generate like hyper-realistic videos. So here is a popular video that you might have seen from OpenAI Sora, where the text prompts say that there's a stylish woman walking down the Tokyo street, and there is things about the background, lighting, and what the person is wearing, and so on. Again, I want to focus on the street is damp and reflective, creating a mirror effect of the colorful light effect. You can see that all these effects that is given in the text prompt are nicely modeled in this generated video. But I want to first emphasize that modeling this lighting effects is very hard. To show that this is a very simple scene that I captured of an indoor living room. There's no furniture. It's a very simple scene. But you can imagine there are so many things going on in this. Like for example, there are windows from which the light is coming through. There are the chandelier, where if you switch on or switch off, the lighting effects would change. There is also a chandelier. There you can see a shadow. And most importantly, as you see, there is a reef off where that is the pixels that are closer to the light source are intense enough, and the pixels that are farther away from the light source kind of tail off. So these kind of effects are very hard to model. Even with simplest tools, it is very hard to disentangle this kind of phenomena, and it is very hard to model. And the other simple effects that you see is that the interreflection may also affect the appearance. So for example, if you see this white sphere, the surrounding objects around it may change its effects. Like you see a green tinge over here, you see a red tinge, and you see a blue tinge because of the surrounding objects around it. Not just about lighting, the interreflection, the way light bounces off the surface may also affect the appearance. So I always get asked this question: why should we care about this problem? Of course, there are a lot of commercial aspects to it. Like it is evidently used in VFX effects, gaming industries, movie industries, and so on. But from pure computer vision point of view, what many people don't know is most of our current state-of-the-art model fails as lighting changes. So here is a example where a scene captured with different lighting setup. Now, if I use state-of-the-art models, for example, one is a normal estimator, another is a depth estimator. As you see, the lighting changes. These are geometry effects, which I'll get into in next few slides. They should not change as lighting changes. But as you can see that as lighting changes, there is a large variance. And these models are currently deployed in the real world, like self-driving cars, robot agents, which is dangerous. What many people don't know is that this model fails as lighting changes. So the question I want to ask is, the generative models that I showed you earlier seems to capture this complex lighting phenomena, but the state-of-the-art models don't seem to understand about lighting. So what do these generative models know about all this lighting, geometry, and 3D awareness? So this is a broad question that I want to ask. And before we get to that, I like to show this cartoon how images are formed. You might have seen this from Crook's, the movie Crook's 2013. You can see that images are like 2D projections of the 3D world. This is oversimplification, but if we also look at a very simple cartoon example, so here you see a simple scene with 4 different objects. There is a spotlight falling onto this. Now imagine I have a camera here, somewhere here, and I take a snapshot. And what you see is this projection of this 3D world on this 2D image plane. Now, in computer vision, what we are interested in is going from this pixel space to understand what is happening in the scene. And what we see is 2D grid of pixels. But what we perceive is 3D shape, appearance, arrangement in space, and so on. So the goal is, can we model all this 3D shape, appearance, and arrangement in space just by using image information alone? And this problem is not new. It has been long studied since 1970s. And this 2 gentlemen, Ari Barrow and Anand.B, came up with this concept of intrinsic images in 1978. What they said is that, okay, let's say if I have an image, we can decompose them into certain parts. What they call is first an albedo. Albedo is something that is independent of lighting, like the color, the appearance that you see, which is completely independent of lighting. The other is shading, that is dependent on how light interacts with different surfaces. So here you can see that for the scene, you can see there are shadows, the geometry effects. These are getting modeled. So this is 1978, so you'll see like a very cartoonish image. I'll show a modern example using this. But to motivate this concept, first you can decompose images into something that is light dependent and something that is light independent. And light dependent components are mostly dependent on the scene geometry, so you want to decompose it into scene geometry. You want to recover scene geometry as well. So you can recover scene geometry using something called surface normal, where for every pixel we want to predict what the orientation is. Like for example, the ground is pointing upward, ceiling is pointing downward, this wall is pointing towards me, and so on. And then you also want to predict how far away each pixels are, or we call it depth. Like from the camera, you want to predict how far away these pixels are. So if we go back to this cartoon image, the very simple primitive image that I showed you earlier, so the intrinsic images that Baron Tenenbaum described would look something like this. So albedo is something light independent, so you see the color of the objects, like the red cylinder, the cyan cone or yellow sphere. And the shading is dependent on the light dependent effects that you see. So if you recall that there was a spotlight coming from over here, now you see that there is a shadow of these different objects. And surface normal and depth are geometry effects, like this red means that it's pointing upwards. And depth is like how far away these pixels are. So darker pixel means it's closer to the camera, and lighter pixels means it's farther away from the camera. Now, the goal in computer vision, one of the goal in computer vision is to decompose the scenes into the scene property maps or intrinsic images like albedo, shading, surface normal, and depth map. Whereas in graphics, it's completely kind of opposite, like the inverse of this. So in graphics, what we are interested in, given this scene property maps, we want to render images. So you can imagine your game engine, take your any favorite game engine. What you have is artists creating these assets that are this color, geometry, and how light would interact with it, and then you render scenes from it. So why this is interesting? Now, let's say if I don't like lighting of the scene, and if I want to change it, I don't want to change. So what I can do is I don't have to change all of this property maps. Only thing that I can change is light dependent effect. So in this case is shading. So for example, I change the shading of it. Now the light is coming from the left side instead of right side. You see that the shadow has moved from left to right. And you also see how the scene is relit now. At the top, you see the original scene. The shadow was coming from, is over here. Now the shadow has moved from left to right. So now what if we can generate massive data using this graphics engine and train our models, and then we may be able to decompose these scenes into all these nice property maps. So we all know that the success of modern deep learning is, what we need is huge amount of data. So we need data, and this is a popular quote from Sherlock Holmes, where you can't make bricks without clay, meaning you need lots of data. And there have been massive efforts over the years to create massive computer graphics generated data set. So here are two such efforts. One is from UCSD, Open Rooms, and another is from Apple, HyperSim, where they curated huge amounts of data by asking artists to create this computer generated data set, where you have this the intrinsic images that I showed you, albedo, shading, depth maps, and normal map, and all other complex property maps, through which you can render scenes. Now you can train a supervised model using this massive data set to decompose these scenes. But the problem with this massive CGI data set is that there is always going to be a domain gap. And it's very hard for them to generalize to real scenes. So here is a fantastic thesis work from Zhenchin Li from UCSD, where you see that these are some of the rendered images that I'm showing you from the data set. What you see is there are rendering artifacts. So in the red boxes, you see that there are missing pieces or the ghosting artifacts. In the purple box, you see that there are missing surface details on the table. And not sure it's visible on the projector screen, but in the orange box, you see that there are patchy artifacts on the wall. Because of this domain gap, there is always going to be, from synthetic to real images, this massive gap is going to create, even with massive CGI data set, it will be very difficult to model accurately. And the other problem that we have is, it's very hard to collect real world data set. Imagine like you want to capture a same scene under different lighting condition, you have to wait like maybe 24 hours a day in order to collect a massive amount of data set. And people have tried this, and it's very hard to scale. And the only data set that is available is this MIT multi-illumination data set, where we have 1,000 real scenes in 25 lighting condition, and it costs like $1 million to collect this kind of data set. And it's very hard to collect data set. So I'm interested in relighting. So the question is, so how can we do relighting, or how can we understand about lighting? And as I showed you earlier, lighting is it's not so easy problem. But I also showed you that generated images show plausible lighting effects. So all these prompts that I showed you earlier, they seem to capture complex lighting phenomena using generative image models. So the first question that we asked was, do generative models know anything about lighting? If they do, can we control it? So the hypothesis that we had was these models learn lighting physics implicitly. Now, can we use generative image models to recover this lighting phenomena? So the generative models, there are many out there, but for today's talk, we'll mostly focus on two of them. One is a popular GAN architecture, or generative adversarial network, Here is a quick refresher too for people who may not know what GANs are. So in GANs, you start with some noise or some noise like a Gaussian noise. You pass through a network, a generator network that generates an image. Now you have a large pool of real-world data set. Now you take both this generated images and real-world images, and now you have another network that is a discriminator, where the job of discriminator is to find whether the image that it gets is whether it is a real or a fake image. And the goal of generator is to fool the discriminator so that the discriminator is unable to distinguish between the fake and real. It is only possible if the real image, if the generated images gets as close to being look like real images. Now, this was in 2014, and this was recently won the Test of Time award at NeurIPS. And 5 years later, until then, the most popular architecture was this generative adversarial network. 5 years later, there was a major breakthrough in generative image modeling space, a network called StyleGAN, where the modification was very simple. Among many, the simplest modification which StyleGAN came up with is that instead of feeding in noise directly to generate a network, you first pass them through some multi-layer perceptron or fully connected networks multiple times before feeding it to generate a network. And they demonstrate there are a lot of advantages to it. First, the first is you get high quality image generation. Like on the left you see is the original GAN generated images. On the right you see a StyleGAN generated images. As you can see that the details have gotten better, the images have gotten sharper, and you can synthesize high resolution images. And what was impressive about StyleGAN is that not just at the time, mostly people focused on portrait images. StyleGAN was one of the first architecture to show that you can generate complex scenes like indoor scenes. And every year, things got better and better. We get to see increased realism. Now, at the rightmost corner, you see that from what we started in 2020 and what we compare to 2023 or 2022, the images have gotten extremely, they get real, and these models have gotten better. The other aspect of StyleGAN is that it enabled, because of the MLP layers that I showed you earlier, it enabled complex indoor scene editing very easily. So the model, the StyleGAN model, because of those MLP layers, it was very easy to manipulate and do this different kinds of editing, like mostly focused on 3D editing. So here are 3 examples that I'm showing you, where in the first one you just rotate the bed, in the right you completely change the scene layout, and in the last one you rotate the camera. So all this was possible because of the simple modification with the StyleGAN architecture came in. Now we saw so many papers after this, there were so many papers showing how we can do image editing. But what we wanted to see was, can we use the same StyleGAN, which people have been using for different editing, for lighting control, which I was interested in. So here is one of the first work, which was published last year at CVPR, where we call it StyleGAN, as the model is derived from StyleGAN, and we are trying to control the lighting. Before I get into the method, I want to first show results. So here is our few generated images, and here are the relighting that we get from the model. So notice the geometry of the scene and the color of the scene mostly remains constant. The thing that you see, the changes that you see are dominantly because of the lighting changes. There are small local changes, if you notice it carefully, near the painting or near the lamps. It's not perfect, but the thing that you see is mostly, the changes that you see are because of the lighting. And this was the first work to show it is possible to relight single images without using any labeled or massive computer graphics generated dataset, all by using just a generative image model. So how does this work? So here is again the schematic of the StyleGAN that I showed you earlier, but a different one. So this is a StyleGAN, simple StyleGAN network architecture. So what you see is you start from simple Gaussian noise, you pass through a bunch of MLP layers for the mapping network, you get some latent code, or what they call style code. You use this style code, pass through another synthesized or generator network that makes an image. So this is the vanilla StyleGAN architecture. The change that we made in StyleGAN is that instead of generating just one image, we generate a bunch of images by adding randomly initialized latent vectors to the style codes and generate a series of images which we call relate images. And the way we ensure these images are relate images is using a pre-trained off-the-shelf model of image decomposition model, which decomposes images into two things. One, a light-dependent component, and another a light-independent component that I described earlier, which is albedo and which is the other is the shading. So now what we want from relate images is that the light-independent component should remain the same because they should not change as lighting changes. So you can impose a simple consistency loss where this batch of images that you get are similar to each other or the variance is too small between them. And the other thing that you want is the light dependent component or the shading should be diverse enough. And what you can do is you can simply enforce that the variance should be high. Using the simple two laws, one a consistency loss and other a diversity loss, you can kind of provoke StyleGAN to generate images that produces same scene but under different lighting condition. We do a small trick along other than these two losses is we also train a simple classifier that takes pair of images. One, the original image, the other is the relate image. And the classifier's job is to predict which latent direction or which lighting direction was applied, a randomly initialized vector. So what we are doing is from the same style code, we just simply add a 512 dimension vector which produces an image. For example, if I add a red 512 dimension vector and the pair of images that the classifier takes in is the blue one and the red one, and the goal of classifier is to predict that the red classifier was applied. So you can imagine there are 4 index, 0, 1, 2, 3, 4, and the classifier is just going to predict, it's a multi-class classification, it's going to predict which index or which lighting direction was applied. And that's it. We only need few hundred images, few hundred generated images. With this simple losses, we can recover these relate images. One important thing to notice is that the generative image model and the image decomposition model are pre-trained and frozen. The only thing that we are learning is this simple classifier and the randomly initialized lighting vectors. So it's like you keep on optimizing this randomly initialized lighting vectors until we get desired lighting effects. Now if we do that, so here are a few qualitative results. So first is the original generated image, and when we apply the lighting direction 1 and lighting direction 2, you see that bedside lamps are switched on. There is a small difference between the two. One is an orange tinge light and other is a white tinge light. And we keep on adding more and more direction. You see different lighting effects. In 3, you see a strong direction light coming from the window. Here the window is not visible, but you can see that there is a strong direction light effect coming from the window. And in the 4th, you increase the brightness of the room, and in the last one, you decrease the brightness of the room. So the thing that was surprising and impressive to us was once we find this lighting direction vector that I showed you earlier, the effects remain the same irrespective of the scene. So for example, if I apply the red direction, it will always switch on the bedside lamp. And if the lamp is not visible, then you won't see any effect to it. So all this direction that I am showing you came from distinct lighting direction vectors. So these are kind of, without using any labeled data set, we find that this kind of emergent latent phenomena exist within the StyleGAN network architecture. So distinct lighting direction means a pattern or a lighting effect without seeing any of these effects. And this can be applied to any generated image which a StyleGAN image would be. I can pause and answer any questions if there is. Yes.
How do you enforce the model to learn the correct light?
We just have this losses.
Here.
One is we want light independent effects to remain the same, and the other light dependent effects should have high variance. And the network, the model automatically figures out different lighting patterns because it has seen millions of real world images, and it knows that, okay, in order to change lighting, either the light coming from the window has to change or the lamps needs to be switched on or switched off and so on. So it automatically discovers these properties. Okay. So Some observations. So StyleGAN can relight complex scenes, and as I described earlier, like modeling this lighting effects is very hard. And in order to do that, you need to know about light sources. Like here, StyleGAN knows where bedside lamps are, where windows are, and it is able to model this direct and indirect lighting effects. So direct is just switching on lamps, and indirect effects, like you can see that as it switches on lamps, the appearance on the wall also changes, not just the lamp. And it seems to interact reasonably well with the scene layout. You don't see like large geometry changes, which is like a common problem when you're trying to do generative image editing. But there is one limitation that all this, the result that I showed you, it only works for generated images. Because the model that we are using, it just starts with, you start from a noise and you are generating image, and we are just editing a generated image. So we cannot apply this to any real world images. So it only works in the synthetic image space.
Just to make sure I'm following. So what you're saying is that StyleGAN has these control inputs.
Yes.
And some aspects of those inputs are controlling the lighting, and other aspects are controlling maybe albedo or
yes,
shape, depth, or
correct.
whatever. How do you tease those apart? So here you're actually controlling the lighting. So you've identified the channel to the lighting.
Correct.
Right. So can you say again how you identified that channel?
Yeah. So the way we identify those channel is just by finding random projections in the latent space, which when you apply will only change lighting effects.
So StyleGAN has distinct inputs, right? It's like various resolutions.
Right. So the style code gets fed into different resolutions. The same 512 dimension vector code gets fed into different resolution.
Okay, so there's one vector, and you're finding projections of that vector.
Correct.
That correspond to, right? Okay.
Correct. One vector that we find correspond to different lighting. Now, if I want to change not lighting, I want to preserve the lighting but change the appearance, what I need to do is I can just swap the losses. I can apply consistency. The lighting effect should remain the same, or the light dependent component should remain the same. Light independent component should change. We do that in the paper.
What you're learning is a projection
of appearance change, and we preserve the lighting effect.
In the style code space.
Correct. And we can preserve the lighting effects. Like always, bedside lamp will be switched on, but you change the wall color or the material properties and so on. And we can find random projections of those as well. So what we are doing essentially here is that these projections already exist somewhere in the high dimensional space of this generative model. We are just discovering them using the simple loss that we use.
To follow up on that, or do you find the projections like manually? Like, do you handpick the projections?
No, we just, it's a hyperparameter, like we find 16 projections and we just look at what those effects look like, and we find consistent pattern in those images. So these are the effects that we find this so these are, it's like a hyperparameter. You choose how many projections you want to find. And as you keep on finding more and more projections, you see that the variance tapers off, like it's like standard bias variance. And if you have like very few, it's going to be biased. So there is a sweet spot between what is the right number of random projections.
So let's say you find 16 projections. Among the 16, you handpick.
Among the 16, I'm showing top 5. You can rank them using metrics, which has high diversity score, which has consistency score based on the losses that you have, and you can rank them. So the things that I was showing you was top 5. So these are not cherry picked or not hand picked. These are the top 5 random projections that we find with maximum effect that we want to see. So first, this, as I said to you earlier, this was the first work to show complex indoor scene relighting. And this was very surprising to us because people have been trying for years how to model lighting effects even with massive computer graphics data set with supervised model. It was very difficult to get these kind of effects with. So then we ask this question, okay, StyleGAN can relight complex scenes, but how is it doing it? Is it manipulating some abstract representations that we do not understand, like Mondrian painting, some Kandinsky, or some complex features? Or maybe it's grounded in something very fundamental that we already talked about, like intrinsic images.
Where is Malevich?
Which one?
Where is Malevich? Black square.
Sorry?
Oh, black square.
Yeah.
It's not here.
Yes.
It's on the right.
Okay. So these are the two. Maybe they are manipulating some abstract representations which we don't understand, or maybe they are dealing with something very fundamental, intrinsic, or maybe they are doing both. So we ask this question, okay, if StyleGAN are dealing something with fundamental physical concepts like intrinsic images, then we should be able to recover them as well. In our follow-up work, what we showed was StyleGAN indeed knows all this complex physical concepts like normal, depth, albedo, and more, and we can easily recover them. So here are results. So first is, I want to show recovered intrinsic images from StyleGAN. Normals and depth are geometry effects where different color represents. So the magenta color that you see here means that the pixels are pointing upwards. Green means that for the ceiling, it's pointing downwards, and so on. For the depth, the bright color that you see it's closer to the camera. The darker color means that it's farther away from the camera. The albedo is light independent effect. Shading is light dependent effect, and we can also segment like where are the lamps. Now, if we compare, this was back then the latest greatest method supervised model at the bottom. You can see that we get like comparable result. Sometimes even the recovered normals are much better as compared to the original image. And also the StyleGAN is able to segment lamps much better than a model that is trained with lots of supervised data. So it's able to segment this. One hypothesis is that since the model has generated these images, it must know where this lamp segments are, and we should be able to easily recover them. So this was one of the first work to show that these generative image models are not just image generators, they are also learning physical concepts or physical properties of images under the hood. And we can easily recover them without using any labeled or supervised data. Okay, so here is another example. Here you can clearly see that when even if the image generation is not complete, here the partial lamp is that the model knows that it is trying to generate a lamp, so we can segment it. So how do we recover this intrinsic images from StyleGAN? We use the same trick that I showed you earlier for lighting, where we have this simple vanilla StyleGAN where you feed in noise image, pass through some mapping network, you get style code, and you pass through a synthesized network to generate images. Now what we do differently here is that instead of finding lighting directions, we find this independent scene property directions. So one that would make normal, the other that would make depth, the third one that would make segment, light dependent component and light independent component. And the way we can do it is we can use off-the-shelf model, like it can be one model, it can be individual models of dense predictors, where you take in synthesized images, pass through pre-trained model that predicts normal, depth, segmentation, albedo, and shading, and you can apply a simple regression loss only to update the scene property directions. All these models are frozen, they are not trained. The generative image model and the pre-trained image models that we use are completely frozen. What we are using is we are using them to guide and find the random projections in the latent space, which when we apply, instead of generating images, we get the scene property maps of the same scene. So here again, what we are learning is this random projections, or we are optimizing for find optimal random projections that when we apply, instead of generating images of the same scene, we get this normal depth albedo and shade. And if we do this with few hundred images, what we find is that we can indeed find this random projections that makes images that looks like something like normal, depth, segment, albedo, and shading. When I showed this to my advisor, PhD advisor, he did not believe this because the generative image model that we trained has never seen this kind of images. They're completely out of domain. The images, the natural images that we see is something like this, and it was very hard for people to believe that it's such a random projection latent space is lurking within inside this model, and it's easy to recover them. But we show that not only we can recover them, and it is surprisingly easy to find. And if you think about images, the way images are formed, these are fundamental scene property or scene intrinsic images that make that when you render them from graphics point of view, when you render them, you get an images. So you can imagine this generative image models are sophisticated rendering engines that are not only learning to generate images, but they are under the hood, they are also learning this complex physical phenomena. If a model has learned to generate high quality images, then it is natural to expect that as a byproduct, it will also learn to understand about or generate the scene property maps under the hood. The next question is there anything specific about StyleGAN? So I just talked about one of the, so always get asked this question, what about other generative image models? In our follow-up work with Shaudan, Greg, and Nick Colkin, we show that it's not just about StyleGAN. Any generative image model has under the hood learns this intrinsic property maps and we can recover them. So here are some results. Here is an autoregressive transformer-based generative image model trained on faces. These models are trained by someone else. What we are using is we are just using this off-the-shelf pre-trained models and we show that we can recover normal depth, albedo, and shading. This is one model. Another model, a bigger StyleGAN model trained again on faces. A StyleGAN model trained only on bedroom images. And at the bottom is a diffusion model, a stable diffusion, the latest, greatest diffusion model. Also learns under the hood this intrinsic images. I'll not go into the details of how we recover intrinsic images from this model, but we use the same protocol which we apply to all generative image models and we can recover them. But important thing to note here is that all these intrinsic images emerge as latent representations in generative image models. And not just one generative image model, we apply this to any given generative image model and we can easily recover them. But then we ask this question, if these intrinsic images emerge as latent representations, why do they have to be image-like maps? Since 1970s, ever since Baron Tenenbaum came up with this concept of intrinsic images, people always thought that they have to be image-like maps. The albedo, shading, normal depth that I showed you earlier, they are all like image-like maps. But why do they have to be image-like maps? If they can emerge as latent representations inside this model, why not treat them as latent variables? And let model figure out what is the right representation. If we restrict them to images, then we are restricting what you can model in just three channel or three-dimensional space. And it may be that it is complex effects, lighting effects that I showed you earlier it's difficult to model in this image-like space. So we tried this idea with Shao, Michael, and others, where we show that, okay, you can treat these intrinsic images as latent representations. And if you just train a simple model to relight, we can recover them automatically. We trained a very simple model. Here are two images, same scene, captured in different lighting conditions. This is from the same MIT dataset that I showed you, 1,000 scenes in 25 different lighting conditions. So at the top, use same scene in 2 different lighting conditions. What we do is we train a simple encoder that recovers a vector which we believe to behave like a lighting. It's a low-dimensional lighting-like vector. And then we also recover a feature map which we believe behaves like an intrinsic feature map, something that is independent of lighting. And you do this with the other image as well. And thing to note is that it's the same model, they share parameters. So it's the same model, 2 images as input, and we recover a lighting-like vector and intrinsic feature map. Now we train a decoder that takes in lighting vector from one image and intrinsic feature vector from another image and combine them to get the relit image, or it should, since we are taking lighting from the top image, the image that we get as an output should match the same as the top image. Now you can impose a simple loss again, like a simple regression loss between the top image and the output that you get. And you can also impose one more constraint, that this intrinsic feature map from 2 different images has to be the same because they are light independent components, so they should not change as lighting changes. Now if we train a simple model, what we find is that we can first generate very good relighting images. to show that here is quantitative results on this very hard MIT multi-illumination that I showed you earlier. At the top, you see a very recent model which was published last year at SIGGRAPH. It's called RGB2X, where it uses massive computer graphics dataset. And it also uses a generative image model. Here is a root mean square error and a structural similarity metric. Root mean square, the lower is better, and structural similarity metric is higher is better. And if we use this our latent intrinsic approach, first we find that we improve the root mean square error by 12% and SSIM by 21%. And if you look at, we first improve by a significant margin. And if you look at relight, we can also relight with arbitrary test scenes. So here you see that the image that we are trying to relight and the target lighting that we are trying to match are completely different. They are coming from different scenes, but still we can relight it. Here the model is able to understand that, okay, we are trying to switch on the bedside lamp and it is able to switch on bedside lamp. And in the bottom you can clearly see that we are going from a low lit scene to a well lit scene, and you can clearly see that here on the spherical ball, the lighting effect that we are trying to match seems to match with the target lighting that we are going to get. But what was surprising to us, or what we found, was that if you recall in this model, what we had was a simple low dimensional lighting vector and a simple intrinsic feature map. And what Shao found out was that if we just cut out this connection, if we zero out, just multiply this with 0 and feed it only the intrinsic feature map, instead of getting a relit image, we get images that just look like an albedo-like map. So here is a comparison of albedo, ours with two different conditions. What I want you to compare it with is the recent state-of-the-art model, which is trained using massive computer graphics dataset. The top row and bottom row are one of my favorite examples. Here what we are trying to do is there is a lighting around the mirror, and our model is able to suppress this lighting effect around the mirror as compared to the previous method, which is unable to suppress this lighting effect. In the bottom row, there is a refrigerator, and you can see all the clear details, like there is a red ketchup bottle, which is kind of lost in the previous state-of-the-art model. And this light independent effect automatically emerges as a property of our training without ever seeing any of these images during training. Any questions at this point? So now coming back to the previous drawback of our relighting, where we couldn't relight real images with StyleGAN, and now we have a model, the latent intrinsic model that I showed you, which seems to not only where we are able to recover lighting effects and relight the model, we can also recover albedo-like effects. So what we did in our follow-up work was we just combined this latent intrinsic phenomena with the powerful image generation model and see if we can relight real images. So here is a follow-up work where we combine this latent intrinsic representation with the powerful image diffusion model to relight indoor scenes. Unlike generative adversarial network, in case of diffusion models, what we do is we start from a simple image, noise it multiple times, and then we recover the original image back. It's based on the simple phenomena that destruction is easy and creation is hard. So if a model learns to create these images, then it learns powerful image representations. So each of this step is learned through a diffusion neural network where you feed in a noisy version of the image and the output that you get is a somewhat cleaner version of the image. You apply this at chain and you do this multiple times, and the final version that you see is a somewhat cleaner images. So this is currently the recent, the most state-of-the-art model that we have, where all this, the Sora models or the mid-journey that I showed you is built upon this powerful diffusion neural networks. Since after diffusion neural network, people have come up with different ways again to manipulate images And one such popular approach is a control net architecture, where control net is a simple conditional diffusion model where you start from an image, you pass through some conditional model like a depth. Here is a depth estimator where you want to predict how far away the pixels are, and you can use this depth map as a control mechanism to guide and generate new scenes that match the same depth map. You can see that it's a different cat, but it respects the kind of the scene geometry. You can notice that there is a table here. Again, there is a background window, and so on. So you generate the same scene with similar layout with a control mechanism. It's a very simple idea, but it helps you guide and control the type of images that you want. So what we did in this work is that we simply combined the concept of latent intrinsic that I talked about earlier with this control mechanism. So what we do is we simply train a simple latent control net. Instead of taking one guidance mechanism, we take in two input. One is the lighting vector and the other is the intrinsic feature map, and pass it through a pre-trained diffusion neural network. And the output that we want is a real-lit image. And if we do that, again coming back to quantitative metrics, what we find is that we can significantly improve from our previous latent intrinsic work. For this relighting task, we are able to improve RMSE by 35%, and we are able to improve structural similarity by 18%. The overall improvement is about 43% on both this metric compared to the previous state-of-the-art method. And if you look at qualitative results, here is the original image that we are trying to relight. Here is the target light that we are trying to match in the second column. The RGB2X, the previous state-of-the-art method, as you can see that it is only trying to change the color of the scene, and it is unable to match the lighting of it's unable to change the lighting of the scene. And if you apply the latent intrinsic, since the scenes are very complex, you can see that it is trying to suppress the lighting. For example, in the second row, it is trying to suppress the lighting that you see from the lamp, but it's not that realistic. And if you apply this, our latent intrinsic with diffusion model, we can see that we are able to match the target lighting. In the top row, we are switching on the lamps. In the bottom row, we are switching off the lamps. And in the third row, again, we are switching on the lamps. We are able to transfer complex lighting from one scene to another. So here are some randomly chosen images from the internet. These are in the wild images. So here is a source scene, and here is the target light that we are trying to match. And the right side you see is the real-lit image. So the thing you should be noticing is that first we convert the nighttime scene to a daytime scene. There's a light coming from the window. You can see that there is a light coming from the window. But I want to focus on one thing. What do you see here? Anyone?
Reflection of the window.
Sorry?
Reflection of the window.
It's yes. There is a reflection in the TV. There is a reflection on the TV, and it's a reflection of the table that you see over here. It seems that this model have learned this complex lighting phenomena in order of second order effects, and only by imposing right constraint we are able to recover this complex relighting scene with all this indirect lighting effects. Yes.
Is there reflection also in the fireplace?
Sorry?
Is there reflection also in the fireplace?
Yes, there is a reflection on the fireplace as well.
So is that?
There is a reflection of the of the table.
Do you think it learned the objects or just learned black? Reflection on black?
It's very hard to say how accurate these are because we don't have underlying 3D model. But first of all, it is very surprising that it is able to hallucinate or it is able to generate plausible relighting effects.
Are the cast shadows correct?
Yes, I was going to point to that. So next thing you want to notice is there are cast shadows. But you want to notice that there's a cast shadow of the TV stand, and then there are also cast shadows from the table that you saw earlier.
Wait. Is that catch theory saying correct or incorrect?
It is plausible. It's very hard to say whether it is correct or not. Lighting is very hard for humans, and it is plausible. I'm not saying that it is accurate, it is plausible. Here is another scene where we are switching off the lamp. Again, light coming from the window. You can see that we are able to suppress the gloss on the table. And then here, again, what do you see over here? Of course, the lamp shape has slightly changed, but there is one more thing going on here. Anyone?
Shadow on the wall.
Sorry?
The shadow on the wall?
Yep. That's right. You can see that there are thin shadows of the lamp pole. Okay, there are more examples, but on interest of time, I'll skip some of these results. So far, I've talked about what do these generative image models know. In the last few minutes, I want to switch gears and talk about what do these models not know. So if you look at these images again, so here is again generated from ChatGPT. If you notice, these images kind of look realistic. But if we pay close attention to it, you can find that there are shadow errors. You can see that the shadow of this person is disjointed. The second one, the shadow of the coffee table does not match the cube that you see over here. There are also perspective errors. Like, since images are 2D projections of the 3D world, so parallel lines in 3D meets at a point called vanishing point. So if you draw parallel lines, like from the facade, you see that it meets at a point. But if you draw more lines, see that they start to diverge. Same thing here. First, you see that there are some lines that seems to meet at a point, and then if you draw more lines, they don't seem to meet. So in this work, we show that you can use shadows and these lines as a cue to tell that whether an image is generated or not. And what we show is that these generative image models don't know projective geometry for now. So here are errors detected by our model. You can clearly notice that the red indicates that there are maximum inconsistency in this area. You can see that our model is able to detect correct shadow errors in both these images. And here are perspective errors. You can see that there are some problems with the parallel lines over here. And we use a very simple model. What we do is we train simple classifier that takes in object shadow cues. Like, for example, here we take an input image and we use a pre-trained model to recover object masks and shadow masks. And then train a simple classifier that takes only the masked images, not even the RGB images, which takes in an object mask and a shadow mask, and train a simple resonant classifier to tell whether an image is real or generated. Same thing, we do this for perspective cues. So here we can recover something called perspective fields, which are dense representation of every pixel where is the gravity of that image and how far away is from the horizon, or how far away is from the horizon for every pixel. So you get a gravity map and latitude map which looks something like this. It's for every pixel. Again, you train a simple classifier that only takes this map and you predict whether an image is real or generated. You can do this for line segments too. You can use an off-the-shelf model to recover line segment. These are like points, so you have these 2 points for every line, and you can train a simple network called PointNet, where it takes in the start point and end point of the line segment, not images as an input, just start and end point of images, and you just train a real or generated image. And if you do that, what we find is that you can tell up to 98% accuracy whether an image is real or generated. So we evaluated 5 top state-of-the-art generative image models like both open sourced and some closed source like Adobe Firefly or DALL-E 3. We compare on with 1 million indoor images and 500K outdoor images. And I said, don't want to get into the details of all the quantitative numbers, but we detect whether an image is generated or real up to 98% accuracy. So here are two my favorite example. I mean, of course, these images are generated, but can you tell what is wrong in these images? I've already given you a hint. In the top row, the shadow looks correct and our object shadow classifier thinks that the image is real. But if we look at the perspective errors or the line, if you draw a line segment, it thinks that the image is generated. In the bottom row, we don't have line cues, significant line cues. But if you look at object shadow, if this image has to be real, it has to come from a planet where there are at least 2 suns. You can see that one shadow is pointing this way and the other shadow is pointing the other way.
Is there also issue with the chair on the right in the bottom image and that it's not actually usable?
Yep.
Yeah, the geometry of the chair.
Yep.
Yeah, so isn't that a more major flaw than the shadows?
Yes, but yeah, we don't evaluate on the shape here. We are just trying to evaluate on the projective geometry cues like shadows or line segment here. But you're right, there are other kinds of errors too, which we can use to it. So coming back to Sora that I showed you earlier, what we find is that even this very sophisticated video generation models also fails to replicate projective geometry. So to summarize, what do generative image models know? Seems like they seem to know a great deal of unexplored knowledge about scenes. They seem to understand the visual world. We can recover physical concepts of the 3D world, but they also make these interesting mistakes like errors in projective geometry. Nadi, how much time I have?
You have 3 minutes.
Okay. So,
3 minutes will be better.
So what's next in computer vision? So we know that this generative model seems to know a lot about it, and if we see the progress in computer vision over the years, from 1960 to 2000, what we had was simple edge detectors like this face detection models that seem to work really well. From 2000 to 2010, we had all these handcrafted features which we use for detections. And then in 2012, we had this deep learning revolution. And ever since that, we have several models that seems to have hit the benchmark where all things have saturated, like object detection and segmentation. And from 2022 to now, what I call this is like a generation era or generative era. And the questions in computer vision have also changed. Like in previous days, we used to ask what images are there in the scene, but today we ask, can we understand and manipulate the world? So for example, here we want to change the static table to something like a dynamic file. So what has changed is that computer vision is slowly moving towards like observational science. So what we can do is we can derive solutions from well-trained generative models. You have a well-trained generative models that learns to generate images. If it has learned to generate images, we can use them to use them to derive solutions that we are interested in. As a sneak peek towards that, I want to just show one work very quickly. It's Visual Jenga. It's a new work which I did over at Berkeley during the summer. This is discovering object dependency through sequential scene decomposition. So we ask, what is scene understanding? Is it about segmenting what objects are there in the scene, or what objects are there in the scene, or how far away is the pixel? But if we understand scene, then we must also understand counterfactuals. That is, what will happen if I open the door, open this window. So as a tiny step towards that, we present a new task called Visual Jenga, where given this scene, we want to sequentially decompose individual objects until we are left with the background. So what we do is what we ask what will happen if I remove this, the top bowl, when I compare to when I remove the bottom bowl. So how can we solve visual Jenga? Again, we use this observational science perspective. So if you Google cup, the images that you see are not just the images of the cup, you also see tables. And if you Google cup, Google table, what you see is images, but you rarely see a cup. So there is an asymmetric relationship between the images that we have. And since this model has trained with this millions of images or billions of images, the model has learned this asymmetric relationship which we can exploit. So we came up with a very simple baseline. So here is another example where cat versus table. What we do is we use a generative image model and just infill different objects. So if we try to replace cat, as you can see that the cat can be replaced with multiple different objects. But if you try to replace table, what we see is that most often we get the table back. So what you see at the top, there is a huge spread, and at the bottom you see there is a narrow spread. And you can use this to rank objects, and we can identify which objects to remove first. So here the answer is we remove cat first. So I want to end by showing a small movie where we apply this simple trick to sequentially remove objects. What you are seeing is first we remove objects and we add them back in a sequential, physical, plausible manner. The complexity of scene increases. Show just the last one. Okay, so this is a complex office scene. This is Alyosha's office. With that, I'm happy to take any questions you may have.
We're way over time, so there's one very quick question. Take it.
Is there any use case you have in mind for this visual Jenga, or like is it a building block for some more complicated tasks?
First, we want to understand object relationship in the scene, like what objects are dependent on each other. So you can potentially imagine we can create like complex scene graphs, and then you can identify what objects are dependent on each other. The second use case is we can teach our robotic agents how to manipulate objects. Let's say if I want to empty your apartment and I want to send robots to do it. As humans, we know that what objects to remove first, but robots don't have this cognitive shortcuts, which it's very hard to. So you can teach robots how to manipulate objects.